A buck regulator is a DC-DC converter which converts a higher voltage potential to a lower voltage potential. It uses a switching element to ensure steady DC output of the required voltage. I am Reshma, and today we will discuss the operation of buck regulator. In this video today, we will talk about the inductor voltage and current of a buck regulator in continuous conduction mode. Let us turn on the switch. If D is the duty cycle applied, then on time is given as D into T total. As we discussed in the previous videos, the energy from the input flows through the switch, inductor, and then the load. Let us apply KVL to this voltage path. We get Vin minus V switch minus VL minus V out is equal to 0. We know that when the switch is turned on, it has low impedance. That means the voltage drop across it is 0 volt. On substituting this in the above equation, we get VL is equal to Vin minus V out. Consider 2 points A and B on either side of the inductor. Now, as the switch is turned on, the voltage at point A is given as VA is equal to Vin, and at point B, the voltage is given as VB is equal to V out. These voltages are with respect to the ground point. Now, the voltage across the inductor can be written as VL is equal to VA minus VB. On substituting the voltages at point A and point B, we get VL is equal to Vn minus V out. We know that for an inductor, the voltage is given as V is equal to L into di by dt. If DIL on is the change in the inductor current during switch on duration, then we can write VL is equal to L into DIL on divided by dt. From the previous slide, we know that the inductor voltage during on time is Vn minus V out. On substituting this, the change in the current during turn on can be written as Vn minus V out into dt divided by L. If D is the duty cycle applied, then on time is given as D into T total. Let us now substitute this in the above equation. We get the on time as Vin minus V out into D into T total divided by L. Hence, during this on time, we can write the change in the inductor current as Vin minus V out into D into T total divided by L. This is not the average or peak current of the inductor. The equation only represents the current change from its initial value. It is the rate at which the inductor current rises when the switch is turned on. It can be observed from the equation that the change in the inductor current is directly proportional to the difference between the input and the output voltages and the duration for which the switch is turned on. It is inversely proportional to the inductance of the inductor. Let us now look at the equations when the switch is turned off. If D is a duty cycle applied, then off time is given as 1 minus D into T total. The diode is forward biased and it gives the inductor current a path for discharge. The inductor current is set to freewheel through the diode. The voltage drop across the diode is the forward voltage drop. Let it be Vf. We know that an inductor always tries to maintain the same direction of the current flow in it. In the circuit too, the inductor tries to maintain the flow of current in the same direction as it was flowing just before turning off the switch. To achieve this, the voltage polarity across the inductor reverses. However, For measurement, we must maintain the same polarity as earlier. Let us now apply KVL to this voltage path. We get minus VL minus Vout minus Vf is equal to 0. On simplifying, we get VL is equal to minus Vout plus Vf. Let the switch be turned off. Consider 2 points A and B on either side of the inductor. The voltage at point A is given as minus Vf, and at point B the voltage is Vout. These voltages are with respect to the ground point. Now, the voltage across the inductor can be written as VL is equal to VA minus VB. Let us now substitute VA and VB. On substituting these values at point A and point B, we get VL is equal to minus of Vout plus Vf. We know that for an inductor, the voltage is given as L into di by dt. If DIL off is the change in inductor current during the off time, then we can write VL is equal to L into DIL off divided by dt. From the previous slide, we know the inductor voltage during off time is given as minus of Vout plus Vf. On substituting this, we get the inductor current during off time as minus of Vout plus Vf into dt divided by L. If d is the duty cycle applied, then off time is given as 1 minus d into t total. Let us now substitute this in the above equation. We get inductor current during off time as minus of Vout plus Vf into 1 minus d into t total divided by L. Hence, during off time, we can write the change in inductor current as minus of Vout plus Vf into 1 minus d into t total divided by L. Here, the current sign is negative because the inductor current is reducing. However, inductor current is not reversed. This is not the average or the peak current of the inductor. The equation only represents the current change from its initial value. It is the rate at which the inductor current falls when the switch is turned off. It can be observed from the equation that the change in inductor current is directly proportional to the sum of the output voltage and diode forward voltage drop. It is also proportional to the time for which the switch is turned off. It is inversely proportional to the inductance of the inductor. In summary, let us assume a buck regulator as shown in the figure. Let us turn on the switch for t on duration. Now, the inductor voltage is given as Vin minus Vout. At this time, the inductor current rises at a rate of Vin minus Vout into d into t total divided by L. Let us now turn off the switch for t off duration. The inductor voltage is given as minus of Vout plus Vf. At this time, the inductor current falls at a rate of minus of Vout plus Vf into 1 minus d into t total divided by L. In this video today, we saw the inductor equations and the corresponding waveforms when the switch is turned on and when it is turned off. We will learn more in our subsequent videos. Until then, let's keep exploring and learning. Thank you.